Okay, so we are still looking at integrating, still working with the trigonometric functions, or circular functions, whichever term you prefer. And so today we're using trigonometric identities. Alright, so some of these identities, when we talk about identities, what I mean is this. Ones that could be useful are, now there's of course the Pythagorean, so sine squared plus cos squared equals 1, and of course you can rearrange that so that sine squared is 1 minus cos squared. And cos squared is 1 minus sine squared. So that's another one of the things that we can use. We can also, there's double angle formulas that we can use as well. So for cos, say cos 2x equals 2 cos squared x minus 1. It's one of the double angle formulas. Now you can then rearrange that to make the cos squared the subject. So if we rearrange it to make cos squared the subject, we would add 1 and divide by 2, and then when we add 1 and divide by 2, we'd get that cos squared x equal a half outside of cos 2x plus 1. Alright, so we might do the substitution for cos squared as the half cos 2x plus 1, and that's more easy for us to integrate than the cos squared. Of course, there's related to the Pythagorean. There's two others that are related to the Pythagorean, and so if we divide everything through there by cos squared, or if we divide everything through here by sine squared, we get two other ones relating to that. So if we divide everything through by sine squared, you get 1 plus tan squared. Is 1 on sine squared, which of course is sec squared. And if you divided it, everything through, so that one's divided by sine squared. But if we divide by cos squared, then what we get is 1 plus cot squared equaling what have I done the wrong way around. I've done it the wrong way around, I don't think. divide by cos squared, you get that one. Sine on cos is tan, cos on cos is 1, 1 on cos is sec. And this one, if you divide by sine squared, you get 1 cot and cosec. Alright, so again, that's another thing that we might use for the substitution. And then, of course, there are some other double angle formulas for sine that we might use. But what I'll do is go through some examples. Alright. Now, of course, with the cos 2x, there's another version there which has got sine squared in it that you could use as well. But for some reason, I haven't written that down here. But anyway, I haven't written it down here. So if we need to use that, we'll get to it. I haven't written it down. I don't know why. All right. Right, I need to fix my notes up. I haven't got the formula sheet in front of me, so I'll fix them up later. All right, examples. Let's look at a straightforward one to begin with, and then increase complexity. So, first one. So previously, if we had things with cos, sine, and we wanted to integrate, we also had, we were letting u equals, say, cos, but we also had sine in there, which was the derivative. Now, in this case, we don't have that. So what we need to do is we need to use one of those identities that we used before. Now this one's got cos squared, and so we need to try and find a version of cos squared where we haven't got the squared in it, that there's something else. And that was the one with double angle, so cos 2x is equal to 2 lots of cos squared x minus 1. So there's a cos squared in there, and there's a cos 2x here. Now cos 2x is quite easy to integrate. Alright, so it comes from sine, and then you've got your dilation factor here, your A or whatever it is on your formula sheet that you can put in. So what I wrote before was that cos squared x is equal to a half of cos 2x plus 1. So what we're going to do in this case is replace the cos squared by this one here, and then integrate. Now this half, it's a factor, I can stick that out the front, and then I've just got cos 2x plus 1 and to differentiate with respect to x. So we've then got a half. Cos comes from sine 2x, and we need to put 1 over our dilation factor. And 1, when we anti-differentiate 1, we get?
Sure. Oh wait, anti-differentiate?
Anti-differentiate.
X.
Plus some constant. Alright, so 1/4 sine 2x plus half x plus some constant would be the answer.
There's a half on the inside.
Which half where?
This
This one?
Yeah.
Because when you differentiate sine 2x. When you differentiate it, what happens? Doesn't this 2 come out the front? Changes to cos. So when we haven't got that here, have we? We haven't got the 2 here. So that's why we need the half. So when we go back, that half becomes this 2. Yeah? And again, I haven't got the formula sheet in front of me, so I'm not sure how that integral is written on the formula sheet. So it might have that there, I would think. All right, next one. Let's do another one similar to this one, not too involved. So tan squared this time. So again, we don't have the derivative of tan there, which is sec squared. That's not in there, so we need to look at some other way of doing it. And now the version of the Pythagorean that has tan in it is 1 plus tan squared equals sec squared. And so now we're going to use that. All right, so we can rearrange that tan squared x to be sec squared x minus 1, and now integrate that. Because the antiderivative of sec squared is tan. So the antiderivative of sec squared is tan x. The antiderivative of 1 is x plus some constant. Alright, so really again with these substitutions that we're doing, just like at all our other substitutions, we're trying to change something that's complicated into a form which is easier for us to deal with. All right. However, we might not always be using Pythagoreans and things like that. So let's have a look at this one. So sine 2x times cos 2x. All right. So in this one, we're not going to use one of these Pythagorean versions, nor are we going to use one of the double angle formulae. Because when you look at this one, sine 2x and cos 2x, is there a relationship or a connection between those two? If you differentiate sine, what do you get? Cos. So in this case, there's a relationship between those two things. So if I say, okay, so let's let u equal sine 2x, and so du dx is 2 comes out the front, cos 2x. So here we've got something that's the derivative, so we're using the same kind of technique as we did before. So from that, we can say that then dx will be du over 2 cos 2x. So our integral now becomes u times cos 2x, and dx is du over 2 cos 2x. What happens to the cos 2x's? They cancel, yes. And so now we've got simply u du.
What happens to the 2? That goes out front.
Good question, because I'd forgotten about that. Good answer as well. All right, so antiderivative of u is u squared on 2 plus some constant. And you've got a 2 there, a 2 there, so 2 2's are 4, so it's 1/4 of sine squared 2x plus some constant. Yes, no, maybe? All right, let's start having some fun. All right. So this particular one. D. Quite fiddly. So we've got cos to the 4. And so we somehow need a cos to the 4 in there. So we need to
Cos squared plus times cos squared.
cos squared times cos squared is correct. So we need cos to the 4 is cos squared times cos squared. Now before, with one of those double angle formulas, so from that cos 2x is equal to 2 cos squared minus 1. So from that one there we got the cos squared, forgot my x was equal to half of cos 2x plus 1. So if we're thinking it's cos squared times cos squared, let's start with that. So if we're starting with that, then our cos to the 4x would be this multiplied by itself, so you've got a half cos 2x plus 1 times by a half cos 2x plus 1, which is 1/4 of a bunch of stuff. And that bunch of stuff, just FOIL, so it's cos squared 2x. You've got cos 2x there, we've got another cos 2x, so there's 2 of them. And then 1 times 1 on the end. So we've now got that.
Why would you use that equation, cos squared x is equal to half of cos 2x plus 1 instead of 1 minus sine squared?
Where are we? Why would I use?
The cos squared x is equal to a half of cos 2x plus 1. that equation there?
Because I'm using this double angle formula. And when
Why,
I
why
rearrange-
wouldn't you use the other formula? The Pythagorean?
Because then you've got a sine squared in there, and you've got that squared, which causes you an issue. How do you, and which is the same here, this power, because I don't have the derivative of cos in here, this power of 4. Because if I had sine there, if it was sine times cos to the 4, that would be simple. So it would be just let u equal cos. So it's because we don't have the derivative of cos that we need
In
to,
the equation, yeah.
in this equation, this original equation, we need to find something where we don't need the derivative of cos.
Okay, that makes sense.
All right, so we've now got this here, and we now need to kind of do something with that. All right. So we're looking for cos to the 4 of x. And now, again, we've got something here where we've got, again, a squared, cos squared. And so we need to have a look and think of how can we rearrange something to deal with this cos squared here that is now an issue. So how can we deal with that? And how we can deal with that is we can use our double angle formula. Because if cos 2x is equal to 2 cos squared x minus 1, if I replace this x here, and I'll say, well, I'm not going to put x there, I'm going to put 2x there, then this is 2 times whatever this here is, and so that then will become 4x. That makes sense? So the thing says 2x is equal to 2 cos x minus 1. So this angle part here is 2 times whatever this one there is. And so while I've done that, well, I've done that because I've got cos squared of 2x, and again, because I haven't got the derivative of the cos squared in there, I need to somehow get it without that, without a power. All right, so now I've got, if I then rearrange this here, then from that, cos squared 2x will be half of cos 4x plus 1. All right, you with me? There's a lot of fiddling around on looking at this. So now what I'm going to do is, instead of this, where are we? I'm sure I've got enough colour. Here we go. So instead of this cos squared 2x, I'm going to put that in there. So if I put that in there, what that means then is my cos to the power of 4 of x is a quarter. Oops, a quarter. Then instead of cos squared 2x, I'm putting this one. And then these other two there, we can anti-differentiate them, so that's all right, I'll just leave them as they are. All right. Then we've got this half in here that's kind of a bit messy. I'd like to get rid of it. move it so I don't have to muck around with that, which I can do by putting it out the front with the quarter, and quarter times half is an eighth. Now, if I'm taking half out, I can't just take it out of that term, I've got to take it out of these terms as well. So that means this coefficient here changes to
1.
taking a half out. A half times what gives me 2? Half times 4. So this coefficient changes to 4. And the 1 on the end, if I'm taking half out, half times 2 gives me 1. All right. There you go. One last step. I can put those numbers together, can't I? Come on, we're having fun here.
Oh, yeah.
So it's 1/8 cos 4x plus 4 cos 2x plus 3. What did you say at the start? It was fiddly. So now there's been a whole lot of algebraic manipulation going around on there. And now we've got something without the squares in it that we can anti-differentiate. The 1/8, I can stick that out the front, can't I?
That makes sense.
Yeah.
Cos 4x
Zeros, yeah.
plus 4 cos 2x plus 3. Alright, cos 4x comes from sin 4x. And at the front here we need
Quarter.
quarter. Cos 2x comes from sin 2x. Of course we need a half there at the front as well. And 3 becomes 3x plus some constant. And then we multiply that. If we now multiply that 1/8 in, you get 132 sin 4x plus 2 over x 1/4 sin 2x plus 3/8 of x plus some constant. There you go, look at that, beautiful. See, I told you it's going to be fun. Alright, so that's quite tricky, that, because there's a lot of manipulation that you've got to do here to simplify that. And the higher that power becomes, then the more complicated it gets. Alright, let's have a look. One more. Alright, this last one. Alright, we had a rule of thumb that we used the other day when we had ones like this. checking. I had a horrible thought I hadn't turned it on. So we had a rule of thumb the other day, was look at your even power and let u equal that. Now, the issue we've got here is that our derivative of cos is sine cubed, so it's cubed. So we just need, because the derivative of cos is just sine, we just need sine. So what are we going to do? Well, we're going to have to do some manipulations. So if we think that sine x is, sine cubed I should say, is the same as sine x times sine squared x. Then we need this one, because if we're going to let u equal cos x, where du dx is negative sine. So we're going to need this one, but we don't need this one. So we want to change this one. Now, because we've got cos here, we think, okay, so how can we change sine squared to have cos squared in it? Now, of course, our Pythagorean, sine squared plus cos squared equals 1. We can write sine as 1 minus cos squared. So if I do that, then I've got sine over x, and then instead of sine squared, I've got 1 minus cos squared x, and then I've got cos squared x. Expand, multiply these two things together. When I do that, I've got cos squared minus cos 4. Alright. And because sine is the derivative of cos, it's going to work out for us. So if we let u equal cos, du dx is negative sine, and when we rearrange that, we have that dx, it's negative du on sine, and so our integral then becomes sine x. Inside that bracket, we're going to have u squared minus u to the 4, which are polynomials, easy to deal with. Then instead of dx, we've got du negative du on sine x. What do we notice there? Sines cancel. That's this negative. What can we do with that? Stick it out the front. Yep. That's negative 1, isn't it? U squared minus u to the 4 du. Polynomial. Yep. U squared becomes u cubed on 3. U to the 4 becomes
u5 on 5.
u5 on 5 plus some constant. Make the going to multiply that negative in and substitute back at the same time, and when I do that, I've got cos x to the 5 on 5 minus cos cubed
So it's still the same thing, it's just
x
yeah.
on 3
Instead of it being in the intake
plus some
it's just
constant.
So you still looking in.
Alright, any questions about those things? Alright. So yeah, again, the same thing with we were doing this, like the idea behind it is trying to find things that you can do to simplify what you've got, to turn it into an integration that's easy. All right, so this one wasn't too bad. The previous example, there was a lot of fiddling around with that. But yeah, essentially that's what we're doing. So, exercise 17.